In this lecture, I want to introduce us to some new reactions that in subsequent lectures we'll use frontier molecular orbital analysis to try to understand exactly why these reactions proceed. So these are, let me make sure my mic's working. Okay, these are electrocyclization reactions. Okay, electrocyclizations look like Diels-Alder reactions, and that's because they, once again, are pericyclic reactions. All right, well, you write that down. I'm just going to just quickly Google a nice definition for pericyclic reaction because yeah, okay, that wasn't as helpful as I thought it would be, but I was going to remind us what a pericyclic reaction was. Let's just leave it at we'll just kind of remind ourselves some features of pericyclic reactions. They are concerted. They involve pi bonds, as opposed to dipoles or charge separated species. And they have a cyclic kind of transition state. I don't think I mentioned this point before, but this is, I mean, just a ring is typically involved as you go from the starting materials to the products, okay? So electrocyclization reactions are a type of reaction that is intramolecular. So these are intramolecular pericyclic reactions. That means they react within the molecule. In addition to being intramolecular, they also involve conjugated pi systems. Okay, so they involve conjugated pi systems, and they are actually classified by the number of pi electrons that are used. Okay, so I want to start with an electrocyclic reaction that is sort of the one that's easiest to do. I'm just going to make a few more pages here. And that is the 6-pi electrocyclic ring closing. Okay, so in a 6-pi electrocyclic ring closing, what we do is we take a hexatriene, and if you'll notice, it's conjugated. Conjugated hexatriene. I'm going to redraw this so it kind of looks, forgive me, Diels-Alder-y. No, it's not a great adjective or real adjective by any means. And I drew that about as small as possible. Sorry about that. So what I did was I kind of rotated the molecule around. If you want to try to track some atoms, these two green atoms are now over here. So I redraw this. It sort of looks like a Diels-Alder reaction. We can actually use the same arrows, and once again, they can go in either clockwise or counterclockwise fashion to give rise to a product. And that reaction looks like this, where we could take the arrows, and I'm going to move them clockwise in this example. And what this does is, if we track where the arrows have gone, maybe I should have made my arrows blue. That's kind of, okay. If I track where my arrows go, they're going to show me the new positions for the double bond. So I'm now going to have a double bond up here. This is from the arrow that's over to the left. To sort of move that double bond over. And then the other double bond moved over in this way. So I have two new pi bonds, just kind of rearranging themselves. And then I finally have a new sigma bond. Okay. Now what I want to show you is, in the first case, we had our starting material, which is not a ring. Whereas our product has a ring. And we call this a 6 pi electrocyclic ring closure or closing reaction. Because we form a ring and we use 6 pi electrons. 3 double bonds or a 6 pi electrons were used. Because 3 double bonds each provide 2 electrons from the pi system, okay? So then if we have 3 of them, we have 6 pi electrons total. And that's where that nomenclature comes from. We close the ring and we use 6 pi electrons to do it. Okay, so we made a ring. It turns out that this reaction is reversible. So electrocyclization reactions are reversible. And what this means is we can actually do a ring opening reaction. Maybe I should call it ring closing reaction, have some parallelism. Okay, so we could have a ring opening reaction. What does that look like? Well, what we do, if I zoom out just a second, is we actually take the product from the ring closing reaction, and we just take the arrows and we kind of go in the opposite direction. We can actually go in either order, but just for the sake of kind of clarity, I want to show that what we're going to do is do the reverse of what we did originally. And so this is called a 6 pi electrocyclic ring opening. The product of this was going to be the starting material that we used previously, the hexatriene system, all in conjugation. So this gives the starting material from the ring closing reaction. Okay, so these two systems are related to each other by way of just reversibility and equilibrium. So we could have a 6 pi electrocyclic ring opening and a 6 pi electrocyclic ring closing reaction. I'm going to stop saying closure. Okay, let's go ahead and just kind of outline this a little bit and describe what kind of reagents can cause this reaction to occur. So 6 pi electrocyclic reactions involve, in the ring closing case, we're going to start with a conjugated hexatriene system. I'm going to show equilibrium arrows. I'm just going to let them be balanced equilibrium, where we have ring closing in the forward case and then ring opening in the reverse case. And the product is this. And we could have the arrows move in either direction. So I could have them go counterclockwise if I want in both cases. You could flip the arrow. The arrow direction is just for us. In terms of the electrons, they go where they go. So we have ring closing and ring opening. So what causes this reaction to occur? This reaction will occur with heat or light. Okay, so if I gave you something like this on a test, and I said predict the products, and I said heat or light, I would probably specify them. I'm going to make that a little bit more legible. I'm just going to rewrite heat or light. Where delta is kind of the alchemist symbol for fire, and then H nu is the mathematical notation for energy from a photon. Okay, so what I'm doing is saying, let's predict the products for what happens here. How you would approach this problem is you would recognize it's a triene. So this is going to undergo a 6 pi electrocyclic ring closure. I'm going to redraw this so it's a little bit more helpful. So I've got my hexatriene now drawn in kind of a Diels-Alder orientation. I use that term super loosely because this isn't a Diels-Alder reaction. It's an intramolecular pericyclic reaction involving only electrons within a conjugated pi system. In a Diels-Alder reaction, we have 4 electrons in a pi system, conjugated pi system, but then 2 electrons from a separate pi system that's not in conjugation with the 4 electrons. Okay, anyway, I'm going to highlight these 2 positions because they map onto these 2 positions of the starting material, which each have a methyl group. You know, I think though I'm just overlooking something. I think this needs to be Z for this to work because I can't just rotate that. I'm sorry, just out of it today. That's my bad. So I should have earlier, I should correct this in the notes. So I'm going to go back and do that in a second. But let's make this Z so that I can actually rotate that around. I can only rotate these 2 atoms, right? Or those 2 bonds. And I should have shown the rotation there. Sorry, thrown off a little bit. Okay. So small correction to the notes we'll have to make earlier for redrawing these things from a 2-dimensional orientation. Or from an extended orientation into something that's a little bit more congested so we can see the reaction. Anyway, let's go ahead and show the reaction now. Have the arrows moving in a clockwise direction. That's going to give rise to a hexatriene system with a new sigma bond here. Then I need my 2 methyl groups which map onto the products here and here. So sorry about that. I missed that that Z requirement. I was thinking about the 4 pi electrocyclic reaction, which we'll get into now before I move back and just correct those notes previously. Basically, this must be Z. This middle atom must be Z. And again, I'm very sorry about that. Okay, so let's do the 4 pi electrocyclization reactions. I'm just going to say this up front. These mostly do ring opening reactions. These mostly do ring opening reactions, but let's look at the equilibrium. These are tougher for students to see because they're so used to using 4 pi conjugated systems in Diels-Alder reactions. So here is my 4 pi conjugated pi system without any substituents added. And you're thinking to yourself, that's just a diene, right? Yeah, so what I'm saying is that what we can do is we can apply heat, I guess I wrote light first, light or heat to this and undergo a ring closing reaction that looks like this. I'm going to move my electrons over here. That's going to connect a sigma bond between these two dotted carbons, and then move a pi bond over here so as to not break the octet rule. That's going to give rise to a 4-membered ring. Before we had 6 atoms involved in the pi system, we got a 6-membered ring. Now we have 4 atoms involved, so we get a 4-membered ring. Okay, so this is my ring closing reaction. And then my ring opening reaction goes the opposite way. Okay, generally, unless you have something special going on, generally this is preferred. Okay, so generally this is preferred. So like me giving you a question like this where I say, okay, now it doesn't matter because the central bond can undergo free rotation. But let's say I give you something like this with the 2 methyl groups and I say, okay, let's apply heat to this. Now predict the products. All right, so this isn't a great question because, yeah, you could redraw this in an orientation so you can see, and this would be the S cis conformation from Diels-Alder terminology. But we could draw this in the S cis conformation and show the 4-pi electrocyclic ring closing reaction. Okay, that's not so great though, because this isn't a reaction that would really occur. Like if you did this reaction, you build a product, but the product has a lot of ring strain. That is to say that it's often the case that in this reaction, you go up in energy to form the product, or this is an endergonic or endothermic reaction. So you have to supply energy to get up here and then you're actually, it's like putting the bowling ball up on the shelf. We tend to want to go downhill or take the bowling ball off the shelf and make something interesting out of the bowling ball once it hits the floor. Okay, so with that in mind, this isn't a super practical reaction. Instead, a better instructor thinking about experiments that you can do would say, okay, let's do a 4-pi electrocyclic ring opening reaction. So where I hand you a cyclobutene with all of its strain, and I say, okay, let's now apply heat or light to this. This is a better reaction because this takes advantage of the fact that these unstable rings can actually release their ring strain through an electrocyclic ring opening reaction, the reverse reaction, to give rise to starting materials for the ring closing reaction, or products that have less strain. That is, we get the conjugated dyne, the conjugated 4-pi system, 4-pi electron system out at the end of the day. So this releases ring strain. And we often go downhill in energy when we do these electrocyclic ring opening. Okay, so the takeaway here is that with 6-pi electrocyclization reactions, the ones that we started with, these actually prefer, and I'm speaking generally here, there's always ways to kind of overcome this and go in the reverse direction, but these actually prefer the ring closing reactions, or the ring close form. That is to say, if you've got your Z hexatriene, you're going to have equilibrium arrows that look like this. Because you form a 6-membered ring, you sacrifice the weaker energy of a pi bond for a stronger sigma bond, and you get to favored formation of the product. So favored at, that's the worst at sign ever, at equilibrium. Whereas 4-pi electrocyclization reactions prefer the ring open form. okay? Where if we have our diene system, we actually have a much more favorable process going in the reverse direction to release the ring strain generated by the cyclobutene. Okay, so that's 4 pi and 6 pi. What about next up 8 pi electrocyclization reactions? So 8 pi electrocyclization reactions often undergo subsequent 6 pi electrocyclization reactions. And this is only in the ring closing case. So with an 8 pi electrocyclization reaction, what we're doing is we are building an octagon, but I'm going to erase one of the sides on my octagon. So it's like a stop sign, but I'm going to erase one of the sides, and then starting from one end, I'm going to have alternating double, single, double, single, double, single to show that I have 8 pi electrons in conjugation. And as I need to remind myself to go back and correct, I've got 2 Z alkenes here. So 8 pi electrocyclization reactions look a lot like 6 pi electrocyclization reactions, except we've got an extra bond present. So what we're going to do is start our arrows at one end, make our sigma bond between the 2 ends of our conjugated pi system, and then push electrons throughout. And then what I'm going to have is a system, and this is with heat or light. I'm going to have a system now that is an octagon that's closed. And I'm going to have double bonds here, here, and here, resulting from the curly arrows with a new sigma bond. So this is heat or light, and this is an 8 pi electrocyclic ring closing reaction. So I formed a new ring, an 8-membered ring in this case, using my 8 pi electrons that are all in conjugation across these 4 pi bonds. And what's cool about this is we can do a subsequent 6 pi electrocyclization reaction. That is the conditions that promote the 8 pi electrocyclization reaction. The 8 pi electrocyclization reaction can continue onward only through a 6 pi electrocyclization event, where I'm going to have a sigma bond connecting the 2 carbons and dots. I'm going to push this double bond over and this double bond over here. It's a 6 pi electrocyclization reaction, except without kind of a telling geometry. I'm not drawing this in such a way that it's easy for you to pick out, hey, what's kind of the final shape of this molecule. So let's do a 6 pi electrocyclic ring closing reaction. Well, if I'm doing a 6 pi electrocyclic ring closing reaction, I'm going to have a 6-membered ring. So I've got a hexagon. So with this hexagon, I now have my blue dots here and here. And I'm going to have double bonds here and here. So this is my 6 pi electrocyclization product, except I can't forget about the CH2 here and the CH2 here. Well, those are just connected to the blue dots, so I just draw them as being connected. So I have to go blue dot to green circle back to blue dot. That actually forms a 4-membered ring. So you get a 6-membered ring fused to a 4-membered ring. Now, can we keep going, and can we do like a ring opening reaction from this? We'll stop here. I'll just say that. We'll stop here. It turns out we don't have a double bond in the 4-membered ring to do like a a 4-pi electrocyclic reaction. It's not to say we don't have options, but so we'll just kind of stop here at this point and consider our 6-pi and our 4-pi system fused together. Okay, so that's an introduction to electrocyclization reactions. What I need to do is just go back and clarify that this earlier part of our notes must have a Z alkene. I just wanted to get cute and redraw. It was right here. Oops, this should be Z. And so a better professor would have recognized that and like tried to draw the extended version this way. You still have to do some free rotation. You still have to do some free rotation to get to the structure that's more indicative of what the final product is going to be. But the free rotation isn't as dramatic because we have to recognize this is Z, not E. Okay, so it needs to be Z, and then we can see our green dots here. Don't know why I didn't catch that. Sorry, off my game. Okay, so that'll do it for this lecture on the introduction to electrocyclization reactions. In the next lecture, I want to look at frontier molecular orbitals and how they relate to electrocyclization reactions and how we can get some insight into which of the products are formed and how effective these reactions are and how effective HOMO-LUMO orbitals are for understanding these types of reactions. Okay, so until next time, I guess I'll see you next time.